about what are the different literature reviews that have taken into consideration of medical knowledge in order to improve the deep learning performance for their task. So this is my team. Our team head is Professor Arjit Sood, who is a professor in the Department of Computer Science. Myself, Akshay Dada. The research scholars Ali and Sonal, and one of our my co-guide and collaborator, Dr. S. Kangaraj. So he is a professor and head at Mehta School of Health Science and Technology. Slide is stuck. So first, the interesting question is why we need medical knowledge, why we need medical knowledge in deep learning. So first is there is a practical perspective. First, the deployment of the deep learning model developed for medical imaging is mostly implementable in medical scenarios. Such like if you have designed something in your lab setup, that must be deployable to the clinical setup, and that must help the clinicians in order to assist themselves in decision making. The research perspective is basically the medical images contain a lot of visual and latent information of biomarkers. Biomarkers, as I have told yesterday also, these are some of the indicators or the clinical indicators that identify the condition of your disease. So there are different biomarkers associated with it. For example, I am working with the knee osteoarthritis. So one of the biomarkers, as we see from the X-ray, is basically the joint space narrowing. So there are two joints. When they touch each other, then then the disease progress or disorder progresses. So this is one of the biomarkers. If I'm working with the MRI, then cartilage thickness obviously is the one of the biomarkers. So that biomarker must be looked into when you're dealing with the deep learning model. If your model is not able to focus on that, then it will be very difficult to get particular idea of the disorder. So these are some of the tasks performed by our lab. So it is basically related to the disease diagnosis, that is a classification problem, lesion, organ, and abnormality detection, basically the classification as well as localization. Lesion organ segmentation, this is what you can say pixel-wise classification of different tissues inside the medical image. Then medical image registration, medical image retrieval, medical report generation. These are some of the tasks which will be considered in future endeavor as a future endeavors. Some of the challenges that exist in medical images are, you can see the medical images mostly are grayscale in nature. Mostly you can see there is a less variation among the different tissues. So you can see the OCT image as well. You can see MRI image as well. So you cannot distinguish between different tissues. You have the similar kind of pixel intensities inside the tissue. So that is what exists in non-differential spatial context. When you are dealing with the deep learning architecture as a convolution operations, so you have the different kernel size and you extract different spatial context at the different locations. So if you are not able to distinguish between different issues as a deep learning model, so then it will be very difficult to identify particular anomaly inside the particular tissue. Let us say consider case of the knee MRI, where you have different the tibia, the femur, and the cartilages. So if you are not able to distinguish boundary between the one of the bones and cartilage, then it will be very difficult for the model to identify disorder in particular bone or whether it is in cartilage. So another problem is a small region of interest compared to the image dimension. If we consider case of the MRI, then we have a small dimension of cartilage as compared to the image dimension. So cartilage is one of the tissue which get degraded in the knee osteoarthritis. So if we miss those cartilage structures and its abnormality, then obviously there will be a problem with our model. So how to deal with that? So recently, one of the review papers have been published that says about how to integrate medical knowledge into deep learning architecture. So I am just overviewing this architecture. paper. So they have identified five ways in which we can integrate. I mean, they have segregated those five ways in different subsections also. So one of the thing is that the training pattern. So as you all know, medical images are not well trained in the deep learning scenarios. So what people have done, they have taken the architecture which is trained on ImageNet dataset. So ImageNet dataset consists of millions and millions of natural image. So these images will be these models will be considered as a starting point to train those medical images. So that is what it is being shown. So first there is a source dataset which is ImageNet dataset. Convolutional layers, fully connected layers will consist of total modeling, and then the source class will be the that ImageNet dataset consists of 1,000 classes. So there will be 1,000 classification. So for your model, if you are doing some, let us say, diabetic DME classification, then you have to take that pre-trained network, which is called as feature extraction. So this is convolution. This is what feature extraction look like. Or you can take the fully connected layers, exclude the penultimate or exclude the last layer, and that gives total number of neuron count equal to classification labels. So you can take whole model as a pre-trained network. Either you can use only the feature extractor, or you have to fine tune that total model, excluding the last layer, into the medical settings. So if you are taking the whole model as a feature extractor, then you have to apply the linear SVM or any another model, so that the model which is present here will only get trained when you are feeding the medical dataset into your source downstream task. So basically here you can see medical dataset consists of less images. So already the trained model will be used here. Then linear SVM will be only trained during that part, and there will be the classifications such as normal, benign, malignant, or anything. Another part is using the fine tuning on the target dataset, where you have the medical dataset. You take the feature extractor as whatever available to you, and then you retrain. Retrain means again you fine tune whatever the weights and biases. It will be again fine tune according to your dataset, and then you classify using normal, benign, and malignant. That is one of the training patterns that is generally observed. Another is curriculum learning. Curriculum learning where you take simple cases first, train using those simple cases, and then you move to the hard cases. For example, in case of normal, benign, and malignant. So benign, whenever there is a benign abnormality associated with the cancer detection, then there will be the boundaries of the benign abnormality will be smooth as compared to the malignant. So it is very easy for model to understand that smooth boundary of the abnormality as compared to the malignant, which is very random in nature. So that part consists of first you proceed for the benign images, then you proceed for the malignant image. This is how the curriculum training works. Then another is the general diagnostic patterns they give the images. For example, MRI and CT. Even though we have the volumetric data with us, associated with us, MRI is a basically volumetric data which have the multiple images of a single patient. So what doctor does is they usually take sample out the random images from this, and they identify, okay, these are the images which are critical for me to analyze. Similar way, we can, if our model can randomly, if your model can clinically sample those images when we are putting that medical images into the deep learning architecture, then we can only focus on the disease biomarkers. So that will be helpful for our training. The next is the area on which they usually focus on. Even though there is a image, I have taken previous image like knee X-ray. I don't have any image right now. But if you see knee X-ray image, there is a, for knee osteoarthritis, there is only the central portion. Image central portion is important. So that means there is a ROI associated with the central portion. So the doctors will not see full image, but they will see the central image. So your model must focus on that part, such as you can use maybe the attention network in order to focus on that single part. So that practical knowledge or that clinical knowledge, at least beginner knowledge, you must take into consideration while designing the model. The next is the feature, the characteristics, structures and shape they give special attention to. For example, the I have in this slide I have taken the example of benign, malignant, and normal. So as benign case, we have the smoother boundaries, and in malignant case we have the rough boundaries kind of thing. So these boundaries will help doctors to understand whether it is normal or benign. Similarly, our model should also take these structural details into consideration while giving the result or while performing the classification task. Similarly, other related information for diagnosis, there are several, for example, if you are dealing with intestinal diseases or if you are dealing with any chest related, such as recently COVID-19. So what doctor does, they have set the patient to do the X-ray. So from the X-ray, they are getting some identification of where the localization, where the abnormality exists in the knee, chest X-ray. And then they have also said to give the blood test or give some associated test. So these are the associated, you can say clinical test that needs to be done in order to confirm the diagnosis. So if you are dealing with such as pneumonia or such as different disorders which are present inside the body, then if there is a presence of another modality, another information such as a view, maybe different views of body like sagittal view, coronal view, and axial view. So you must consider these views also in order to find out where the abnormality is. So I will be moving to the next slide. So in the next slide, we will be talking about 2 points. One is a training deep learning model with disease specific descriptors. As I told, so we need to take into consideration of the structures of whatever present in the given abnormality. So in one of the paper, like Fuse PhD, so they have considering the malignant and benign lung nodule. So initially they have the CT images. So the CT images as consist of many of the slices. So these slices correspond to the single patient. So these slices are segregated and a localized tissue or a localized part is being cropped, and this cropped part for this shape analysis they have taken GLCM based texture features and Fourier shape description. So these 2 points they have taken. So basically GLCM feature extractor builds a correlation matrix in particular direction, such as this 45 degree, 90 degree, or maybe 125 degree. So these correlation matrix of particular pixel with the nearby pixel. So this correlation is basically will then this correlation will be identified based upon 4 parameters, that is structure, shape, boundary. So some of these matrices will be put inside the model to identify the condition of the disease. Another is the Fourier shape descriptor. So Fourier is basically you have Fourier domain. So since you have the image, so you transform it to the Fourier domain and you identify what is the structural patterns of particular nodule in the given image. If there is a malignant tissue, obviously the Fourier description or Fourier shape description will have the higher values as compared to that of the benign. So you have the high frequency component more in the Fourier domain, and for benign you have the low frequency component. So all this information are aggregated using another network, that is Arabus, and then the classification is being performed. So this is general overview how you can integrate those models. In addition to that, they have taken also deep learning feature extractor to conserve or preserve the different location information into the final decision. So next is utilizing attention mechanism for guiding the classification task. As I said, so in a whole image there will be some part which will be important to us. So that part will be identified with the attention mechanism. So in this case, we have the OCT image, some eye-related disorder. So we have Duchenne's, we have CLVs, DME, and normal. So all these abnormalities are associated with the eye, mostly related to macular degeneration or macular portion. So at first the image is passed, OCT image is passed, then they use the convolution to transform into the non-linear, you can say, identify initial features. These features will be mapped as a feature map. So you can see the above is the feature map. In addition to that, they have identified the lesion where it is present in that lesion, and so they have made the attention map of that lesion. So they have fused, they have multiplied this feature map and attention map, and they have generated a lesion aware feature map. So these lesion aware feature map are repetitively passed inside that lesion attention module. So these the purpose of making this lesion attention module more in numbers is that to make it more concise, like identify the regions in a more concise way where the abnormality is. So after they have maybe they have experimented in that way. So we have two lesion attention module, and then there will be classification layers, and then there will be classification. So this is a general overview of how you can apply the attention to the deep learning model to identify the location based descriptors. Then we have the detection case in which we have utilizing image under different settings, multiple views, modalities, maybe additional slices for computer vision tasks. If you have, I have already said, if you have associated information with the model, such as we have the different views, maybe this indicates the axial view. Maybe if you have the sagittal views also, or maybe the different sequence details. So each MRI or CT have many of the sequences. As if you know, if you have worked with that, so each sequences will have a different set of parameters. So in some of the settings, the tissue will be more brighter in nature. In some of the settings, the tissue will be darker in nature. So in those, all this information will adds up the value of deep learning model in order to understand the disease descriptors. So in that case, so they have used the different sequences of the CT images. They have passed into the CNN feature extractors. So all these three independent feature extractors were there to get the features. They have concatenated all the features, and then they have performed a position aware modeling in order to find out the features, in order to get the feature map differently. I could not able to see it. Then the feature map, the concatenated feature maps, they have applied this attention, that is channel wise attention module. To get attention will give you the location at which the model must focus on. So throughout all the feature maps, we have a channel wise attention. That means the channel which are important for the classification, as well as if we have the spatial attention map, then it will identify the spatial location at which the model should focus. It may be in a different channels also. So here they have used the channel attention, and it means it identified the channels which are important for our model. Then these channel, then the attention, then the feature extracted after this attention will pass to the region-wise pooling network. So region-wise pooling network will make a bound, will make a, you can say, guesses of where the abnormality will be present. So these bounding boxes will be of random in nature. So they will have any random size. So in order to that is called their proposals. So these proposals means their abnormality may be present in that. So these proposal will pass to the ROI pooling. ROI pooling will give you the similar or same shape of features. So if you have the different images, you will get the different feature vectors. So ROI pooling ensures that each feature vector must be of same dimension. So then the ROI features will be passed through the classifier and regressor. That is general detection networks output. So you will have classify whether the normal, whether the tissue is benign or malignant, or the identify the location of the bounding box through using regression. Similarly, in breast tumor lesion detection, we have different views. That is called they have called it aligned images. So we have the mammograms, which integrates bilateral information. We have the two different networks for identification of features. So here the missing information that is a feature map basically. So these feature map are passed through the region pooling network to identify which of the regions are, to generate the proposals. Then these proposals along with the original feature maps are passed to another you can say multiplied product to get another two feature maps, and these two feature maps will be added together and passed to the mask head and box head. So basically, this is how you can use different information in order to make the prediction stronger. Then another part is utilizing loss function as a regularization term for fine tuning the segmentation mask. So initially, if you know about the unit is a basically a backbone architecture which was presented in 2015. It works well with the biomedical data. Many of the architecture such as the attention unit or you can say unit plus plus NN unit. So these are all use this unit backbone as a main backbone model. So basically, if you have images, a medical image, then you pass to the unit for a tissue segmentation. You can see the segmentation results here. Gold standard indicates the ground truth, which are actually present available with the original data set. So you pass this segmentation mask as a coarse mask. Coarse mask means first phase of segmentation will not give you the exact results. So you treat it as a coarse mask. Then you pass this coarse mask to another convolution neural network, which will give you the loss function, which will act as a loss, we can say, loss model. So this segmentation mask along with the ground truth, you pass it to the another encoder decoder type of network, and you calculate what is the loss exists between the feature set, two feature sets. So if you have ground truth, if you have original coarse mask, then you identify what exactly the loss exists between the feature of these two sets. So that is called the shape reconstruction loss. So then you add those segmentation loss such as maybe the dice loss or any related loss maybe related to that. You make it another term. So this total loss function that they are called SRNN. So these SRNN will be added another with the loss which is calculated based upon the encoded representation. So you have the encoder, you have the decoder structure. So you have the representation, encoded feature representation. So you also calculate, you pass you can get the encoded representation of the ground truth. You can representation of the predicted map. So you calculate the loss between these two. They are called as an SC loss, and finally total loss function is being propagated. So what is the purpose of adding the loss function here as a loss model as a in the model here is to get what is the structural details of the particular tissue. So as a convolution, in the convolution you have a different hierarchical convolution. For example, you will in the when you pass your image to the convolution, you will get low level features and then high level features. So initially when you pass to this, so model will also learn what is the low level features in the segmentation map. So low level features means related to the edges, related to some of the points, related information will be seen by the encoder decoder network. Similarly, what is the age information of actual mask that will be learned by the model. So it compares what is the missing part in that age information as a you can say in the feature extraction skill, and then it will the loss function will be added and the model is trained in that way. So another is utilizing localization network to locate small tissues for fine tuning the segmentation mask. So basically, you have image, let us say input city volume, passed to the some network. They are calling it the SNet. From the SNet, you have localized a small tissue. So this small tissue will again pass to the ROI pooling network to get the feature vector, and then small tissue segmentation network is you can say pass to the small tissue segmentation network, and then you will get some kind of prediction. So you have the actual city volume, you pass it through SNet, you will get some of the large organ score. So large organ, you can say segmentation volume. So you add those segmentation which is obtained from this detection network to the original network and the fuse again. So what it will give? First one, previous slide. This one.
my doubt is actually you are giving the MRI images, but the unit model. So unit model will be given finally like the segmented images like ground truth. So in that you are saying like that suppose some losses will be there. So in order to finding that loss actually what kind of information losses. So that's why you are sending to the other model to find the losses. Finally you are adding the losses. So my doubt is like why we are going to give the other model like if you have to adjust the weight now like the unit we can adjust the weight we can reduce the loss now. So why we are going to connect the again the model then why you have to add the again. So that's my doubt.
So you are saying why to use another model for segmentation refining?
Yes, yes.
So actually, what happens in unit also? So the problem faced by the unit is it does not works well with the small tissue segment. So we have the when we have the encoder and decoder representation, then while encoding, there might be chance of losing some information that might not be perceived as even if you apply the skip connection. So these small structural details will be missed by the unit. That is, that is a limitation of the unit. So that is why we are additionally adding those another convolution layers in order to find what is the structural details like age related, point related information from that feature, from that you can say core segmentation map. So in that you will get the segmentation mask. So from the segmentation mask, we are finding out those ages and find out those information. So we are not directly utilizing in MRI in that case. So we only have those segmentation map with us. So it will be better if model only focus on the segmentation mask. So that is how it reconstruct. Identify at which feature level it has lost the information. So it identifies the loss between the feature set.
Okay, through the like we are getting the segmented output and actual ground truth images.
Yes.
You're giving to the CNN.
Yeah, we are giving to the CNN. Like, so okay. It identified the difference of suppose if you pass it to the CNN, then it will extract the features obviously. Yes. Then you will have some vector representation there of the predicted map. You have the similar vector representation of ground truth. So you consider ground truth representation as your reference. And you calculate the loss. You subtract that and you calculate the loss between that.
Okay. Got it.
Understood?
Yeah, understood.
In our lab, we are currently focusing, as I told, this is diagnosis, detection, then segmentation, and medical report generation. So right now we are working on classification of knee osteoarthritis using gait data. So gait data is nothing but the motion related data. You have the different parameters related to the kinematics, kinetics, then spatiotemporal parameters. Mostly these are related to tabular and signal related parameters. Another task we are focusing on medical report generation of chest X-ray using vision language model. So this is the task we have started just last year. So we will be using it in order to identify different anomalies. If you have the reports with us, that is already being there with the online repository, and we have the images associated with that. These are the past works we have published in different conferences and journals. So these are the list of that. So I'll be just giving you brief idea about the paper we have presented recently in last year's December. So this paper is basically made sim. So basically we have MRI volumes with us, and we have corresponding labels. So we have the three labels associated with that. One is the abnormality, another is the meniscal tear and ACL tear. So abnormality is nothing but it can conclude different abnormality like as BME or maybe the knee osteoarthritis and other related abnormalities related to the bones, knee bones, tissues. Meniscus is basically the tissue which is present between. If I show the image, then it will be clear. So here you can see. So basically this is you can see knee image, sagittal knee image. So we have the femur, we have the tibia. So these are the two bones. Maybe you can see in black in color. And we have cartilages present in between the two bones. In between the cartilages, there is a meniscus present. So you can see the meniscus, which is a very smaller in dimension as compared to that of the image. Then if it tears down, then it is called a meniscal tear. So it may be because of the sports injury or maybe because of age-related factors associated with it. Then we have ACL tear. So basically, anterior cruciate ligament is present. So this is the ACL basically. So this ACL is present in the intermediate region of the knee volume. So if we have the MR, so we have knee MRI of different, uh, you can say different slices. We have, if we take the 40 slices, then at 20 to 25th slice relatively, the ACL is present. So ACL is nothing but the, you can see in the middle of the image, there is a the portion called anterior cruciate ligament. So this abnormality associated with this is called as the ACL tear. So for that case, three abnormality labels we have, and we have the binary classification task. So three labels and two classification tasks. So initially, we have taken the input MRI volumes. You can say from I to I plus n, I minus n. Similarly, for I will be explaining the entropy maps. First, these MRI volumes are passed through the model. For passing through the model inside the CNN backbone, we have randomly shuffled the slices number. Suppose if there is a ith position, there is a ith slice at a particular position, then we shuffled it to some different position, location. We randomly shuffled. This shuffling is not basically for the training set. This is a random in nature. So any of the patient information we are passing to the model, it will not be similar to each of the volumes we are passing. It is random in nature. So this is passed to the CNN backbone. So here we have used the AlexNet as a simple backbone. So these AlexNet will give me the slice features. So these slice features, it will be passed to the multi-domain feature cross attention network. So I'll be explaining what is that. So in order to get the context of the information, whatever we are presenting to the model. So as I have shown you different abnormality associated with the MRI image. So these we found out that entropy maps, such as these entropy maps, will guide us to get accurate location of the tissues, abnormality present in these tissues. This is just you can say studied offline. I mean, we have experimented and studied it. So basically, similar way, we have the entropy map of each of those slices. So these are also randomly shuffled in the same way as we shuffled the MRI volume. These are also passed through the convolution network. We get the feature map of these entropy maps. These are also passed through cross attention network. So in cross attention network, we have the two inputs. One is coming from the slice feature, another is coming as the entropy feature. So initially we pass it through layer of convolution network. Then we consider the you can say slice feature as a query because we have to preserve that image information, and we consider this entropy features as a key and value, and then we perform the cross attention. So you will have the cross attention. That means when you have the vector associated with value, key, and query, initially you multiply those query vector with the key vector. So it is nothing but the vector multiplication. The vector multiplication of query and key, it will give you another metric, another vector. So this metric or vector will be again multiplied with the values. So this multiplication will give you at what vector values, at what point you have to attain for particular disorder. I mean, any multiplication will give you the point at which you have to focus particular region. So it will finally this map is linearly projected using 1 cross 1 and then added with the query to get the final vector representation. So this vector representation is accumulated or we have find out for the different slices, like I minus 1 and I plus 1 slices. All this information we have passed to the ByGRU layer. So ByGRU will identify what is the correlation, what is the association of its previous feature map and next feature map. So it will enhance the feature representation of the I slice. So that is the intuition we have used. That is in a bidirectional nature, means both like forward and backward. It will identify the correlation. So these fine-tuned feature map we pass to the feed-forward layer, and we perform the binary classification here in this case. And this is basically we considered it as a pretext task. So pretext task consists of binary classification of critical and non-critical. So why the intuition we have used the critical and non-critical here? Because we see the localization of these anomalies. So if we take the consideration of the ACL tier, so ACL tier is mostly focused on 20 to 25 slides. If you take the 40 slides as an information, so these are present at particular locations only. So these locations we consider as a critical slices. So here you can see critical slices. These endings, these slices are nothing but middle slices are critical slices. These initial ending slices are of no use. So we have discarded this information. And the rest of the slices we assign as a non-critical. So this classification we have performed. The advantage of doing pretext task is model will learn what are the differentiation between critical and non-critical slices. So this information or this encoded, this trained model we are directly going to use in the downstream task. Downstream task is nothing but classification of ACL tier, abnormality, and minuscule tier. So this is the final result of our model. So this pre-trained model, so we have fine-tuned it using fine-tune in the downstream task. So this input, in this case, we do not shuffle because the model is already trained. This spatial inter-slice learning model is already trained in kind of robustly trained using different slices, and then these original MRI images along with its entropy counterpart, we pass it to the AlexNet feature extractor. It will give the different features, and again we use pre-trained model, that is MDFCA, and we'll get another spatial feature map. So this spatial feature map will be used as an input to the bidirectional GRU with the previous and next feature map. Again, we will get final feature map. So these two spatial feature map and you can say slice-wise feature map, these are intra-slice feature map, these are concatenated, and finally we will get concatenated feature vector. So this feature vector will pass to the feed forward layer. Feed forward layer is nothing but connection of many of the nodes in a even multi-stage fashion. So this will give finally the classification output. So this was the total schematic of our presentation. So these are some of the results which we have obtained using the training. So previously we have mRNA dataset, which is a repository of MRI images in which specifically focusing on the abnormality condition. It is a Stanford database. So they have given a classification along with the labels of ACL tier, abnormality, and minuscule tier. They have also proposed mRNA as architecture. So the results are being shown here. So clearly, our proposed model with the SSL, I mean with the self-supervised learning, achieved a better result as compared to the previous schemes, such as the LNet, SKID, which is recently proposed. Then also we have shown TSNE plot. So TSNE plot will give you the location. I mean, give you the visualization of your how your feature are being how your you can say feature vectors are being clustered. So basically, if the clustering of similar kind of you can say if the intra-slice intra-class clustering is compact, that means if you have the different images of same class, and if you are finding out the feature of that images, then they must cluster together. So if the clustering ability of that images of same class is compact in nature and intra-class variability, intra-class separation, that means the different class must be separated from the first class. So this intra-class separation is good. Then your feature extraction part is good. So that is how we have showed. So we have showed the different two classes. Since we have two classes, we have showed the clustering ability in case of acyl tier, abnormality, and musical tier. So we have got better clustering, compact in nature, and you can follow the results. So this is it from my side. So if you have any questions, any doubts regarding medical imaging part, you can ask me or you can reach out to me at the LinkedIn or website. Uh, I'm open to questions.
Thank you, Akshay, for your wonderful talk. Round of applause for providing us lots of information about how biomedical imaging is, why is it important, and what are the different techniques which have been used in existing literature as well as in the multimedia lab at IIT Guwahati. We'll now be taking some questions offline first. Does anyone have any question?
I have a question.
Yeah, please give a mic to her.
Why we are doing that downstream task? What's the importance? Like
downstream task, basically we have performed the pre-text task in order to train the class, in order to train the feature extractor and classifier. So downstream task is our target task for which we are doing the pre-text task.
What is the benefit of doing that task?
So basically, pretext, the utilization of pretext task is to train the model, train the classifier, train the feature extractor in a better way. If you give me suppose 100 images directly for the downstream task is nothing but, let us consider that case, ACL tier, meniscal tier, and abnormality. So if you pass those 100 volumes to the model, then the model will not, at first, it will not give you the better result. I mean, I have shown in the previous slide also. So these 100 images, if you pass previously, if you know some kind of basic information about the identification of, let us say, critical and non-critical in nature. So which slices are critical and which slices are non-critical. So at this point, pretext task, the model has already seen those images previously. So it has already find out the features. I mean, it learned how to find out the features from those images. So similar images we are passing out for the different tasks. So if the model is already know that how to extract the information from these kind of images, then model will perform better, obviously. Because suppose if you have learned one subject, again if you revise that subject, it will be easier for you. Similar way, if we have given some information to model at first for the different task, and then if you pass the model for our target task, which is the main task, then the model has already learned the basic information about the images. That is the intuition, and you can see also in the result. So without SSL, it is giving not very good result. You can see in accuracy point of view. So almost 6 to 7% improvement is there. So that is the intuition of behind doing the pretext task.
Okay, I hope it got answered. We have another question.
Actually, my doubt is like I want to create some prototype, like instantly, suppose giving us some retinal images to that prototype, like regarding using Arduino and Raspberry kind of some kind of kits. Like, is it possible like using that? Can you give me some idea for that? Like in my area, everyone doing like theoretical research only. Still now they didn't do any creating the prototype. So I am thinking to create some prototype. So like nowadays, like the ophthalmologists are like very lack to finding a retinal kind of disease. So that's why I am planning to create some prototype. Can you give me some idea for that? So how should I go for that? Like I don't know. Earlier I was working in a Raspberry Pi. So for the retinopathy detection. So can you give me that? Now I am like looking for a microaneurysm. It's earlier stages of diabetic retinopathy. So how much I finding the earlier stages it can prevent for the diabetic retinopathy and diabetics from the patients. So that's my doubt.
So first of all, I did not work in fitting the model into the small setups like Raspberry Pi because you need to have a quantization. I mean, if you have a large model, that obviously it will not fit into the Raspberry Pi kind of thing. So maybe you can look for the different quantization techniques, or the tiny ML is also there. So you may read and look for that. So we usually work in some kind of GPU environment. So that is a limitation we have.
Any other questions? Offline from anyone? Online, do you have any question?
Yes, offline question is there. What is the approach for listen volume calculation on brain MRI data? And what basis do we identify the slice that can be used for volume calculation?
Mostly the slice information, I mean, what are the important slice information? This is consultation with in consultation with the doctors only. So, I mean, if you have any basic knowledge of how the brain slices, what are the critical slices for the diagnosis is important, then you may proceed with that. But usually it is in consultation with the doctor or any medical practitioner. You will get to know all the basic information from them, and then you process how to process in deep learning model. You have to look how to automatically select those slices. Concerning the volume calculation, one of the question was volume calculation to that. So basically, volume calculation, you basically for my case, I work in volume calculation when I have the segmentation map with me. Suppose in the data set, you have the segmentation map of particular tissue. Then you take those segmentation map, you apply the image processing techniques. So image processing, which is applicable in very good manner using OpenCV package. So in the Python, you have to use those OpenCV package. There are different commands like to find out the contour, find out the area of the contour, perimeter of the contour, then a volume of the contour. So all the packages are inbuilt inside the OpenCV package of Python.
Next question. How do I select the number of slices before feeding the model on 3D MRI?
So selection of slices, I mean, it is very trivial question because selection of slices obviously depend upon what medical practitioner, what input medical practitioner will give. But generally, if you have different number of slices, let us say in some patients we have 30 slices, some patient you have 50 or 40 slices. This problem generally exists in medical scenario. Then you may feed all those slices, all the maximum slices, like 50 slices. According to that, you construct the model so that model will take 50 all of the slices, 50 slices. And whenever there is 30 slices, you add 20 black slices. Black slices means this is the slices which have no information. So total input volume, input size will be 50. So 50 throughout for all the patients. How to get that 20 additional slices? The PyTorch we have inbuilt collate function. So collate function will adjust what are the missing information or what is the shape, I mean mismatch in shape. So it will automatically adjust and it will feed those all of the slices into the model. So that is the part. If you take the maximum slices, then it will be as an initial perspective, it will be good. But if you are to focus on critical slices, then you have to consult with the doctors and you have to come up with some logic.
Okay, any other question?
No, online is not there. Offline, any question is there? Anyone?
No. Okay. So thanks, Akshay. Again.